And in the previous lesson, like how you've reviewed, we introduced physical equilibria, okay, where we saw different concepts like a solution, a binary solution. Then we talked about volatile and non-volatile solutes in a solvent. Then we saw how the boiling points and vapor pressure are going to vary in if a solvent has a volatile solute and if a solvent has a non-volatile solute, how the boiling points are going to vary. Then we talked about an ideal solution, okay? An ideal solution where one of you was able to give an example that an ideal condition, it's like when the school is saying, is advertising, it be like all students will receive uniforms on the day of reporting. Now that's ideal. Ideally, that's how it is. But in reality, oh, you can even spend a month at school when you don't have a uniform. So that is an ideal solution and a real solution. So we talked about the Raoult's law, where we are able to see that an ideal solution is that solution which obeys to the Raoult's law. And we made a conclusion by getting this formula from the Raoult's law, that if you consider the partial vapor pressure of an ideal solution, it must be equal to the mole fraction of one component times its pure partial pressure at that particular temperature, then plus the mole fraction of another component times the pure vapor pressure of that component at that particular temperature. Where we are able to agree that if you get the mole fraction of one component, and we did some calculations, okay, we add the mole fraction of another component, then we should get 1. So these two equations, they are magic bullets as far as these these calculations are concerned. And you were able to do the first example, and you did this trial question, and then I gave you homework, okay? And this is the homework that I gave you. And it's good, some people sent answers, and it was really good. And actually, those who sent answers, they had correct answers. And others who didn't send, so I don't know what happened. But always endeavor to contact the teacher so that the teacher can see what you've done. So now this question was some cool question, which says they have given you the vapor pressure of ethanol at 20 degrees Celsius, right? And I have told you that it is 46 millimeters of mercury. Now that is ethanol, okay, at 20 degrees Celsius. Whereas that of benzene at the same temperature is 75.2 millimeters of mercury. And I have given you the mole fraction of benzene in the mixture of benzene and ethanol. Really? Such a simple question. And I want you to calculate the total vapor pressure of this mixture, which contains 0.09 benzene. And so if benzene is 0.09, then what will be the mole fraction of ethanol? Just get 1 minus 0.09. Okay? So from our formula, I hope you are able to do that. So from our formula, which is P, which is equal to the mole fraction of benzene times the partial vapor pressure of benzene at 20 degrees Celsius, because that's what we want, at 20 degrees Celsius. And we add there the mole fraction, okay, of ethanol, okay, times the partial vapor pressure of ethanol at 20 degrees Celsius, then we should get the partial pressure of benzene. Sorry, of this mixture at 20 degrees Celsius. And it was that simple, guys. Okay? It was that simple, guys. So if we substitute, just substitute, we shall have our P. The mole fraction of benzene it's 0.9, 0.09. Okay? And the partial pressure of ethanol, of benzene, it is, where is it? It is 75 millimeters of mercury at that temperature. Yes, we shall write 75.2 millimeters of mercury, and then we add so 1 minus 0.09, this is 0. Our answer, I think, is 0.91. So we shall have 0.91 ethanol, and then times the partial pressure of benzene, which is partial pressure of ethanol at 20, which is 43.6%. So if you calculate this, you come up with the partial pressure of benzene. Guys, what's the answer? Let us hurry up. It is 46 point
Point four four
point
four
four four
four four triple four.
point 444 milligram millimeters of mercury. So this will be the partial pressure of this mixture, okay, that has 0.09 benzene and 0.91 ethanol. Now the part B says we want the mole fraction of benzene in the vapor. So how are we going to get the answer? So what is the mole fraction? How are we going to calculate the mole fraction of benzene in the mixture? So you have the partial pressure, okay? You have the partial pressure of 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 benzene. So they have the partial pressure of the mixture. And remember, these, they are non-volatile. So each contributes independently. Okay? So if you get the partial pressure, can't you get the mole fraction of benzene? Yes, you can. Somebody to give it a shot.
We get the
Uh-huh.
we get that partial pressure of we get the partial pressure of benzene
Mm,
over the total partial pressures of benzene and ethanol.
mm,
So we shall get this product of 0.09 times 75.2
mm,
over 46.444,
mm.
and we get the value.
We get the value. So what is the value? So anyway, anybody calculating to give?
0.1456.
So somebody has 0.1456, and it's a mole fraction, so it doesn't have the values. So basically, these calculations, they are really friendly. Okay, they are really friendly and so easy. So let's check. Let's talk about the boiling point curves. Okay, somebody you can mute. You can mute, or in case you have a question, you can still ask. So now the other one, it was a vapor pressure composition curve, where you here you have the vapor pressure. Okay, you have composition or percentage composition. Okay, percentage composition, and then you have the vapor pressure. Okay, and here you have the vapor pressure of, and you mark maybe this point as the pure vapor pressure of A and vapor pressure of pure B, and then you draw the vapor pressure composition curve. Okay, and it's an ideal solution, which means it is going to vary, okay, as observed. Now that was the vapor pressure. So how is therefore the boiling point of such a solution going to vary? So remember, the solution with high vapor pressure at a particular temperature becomes a volatile if you have component A and component B, and at 20 degrees Celsius, okay, the vapor pressure of A maybe it's somewhere here, and the vapor pressure of B, it is somewhere here at 20 degrees Celsius. It means that component A will have a high boiling point, okay, and component B will have a lower boiling point. Why? Because we agreed in the previous lesson that the boiling point, okay, it's that temperature at which the vapor pressure of a given substance is equal to the atmospheric pressure. So for you, if you have the highest vapor pressure at a particular temperature than the other, it means you will achieve the vapor pressure which is equivalent to the atmospheric pressure at lower temperature. Hence you boil at lower temperature than the one which has. So therefore, when you are sketching a boiling point composition curve, obviously it's a curve, or it's a graph of temperature at which a mixture boils when plotted against the composition. And where is my curve? I think it's here. Yeah, it is here. So if you increase the temperature, then the vapor pressure of both liquids in the mixture increases, whereby the volatile, or the vapor pressure of the one which is more volatile, it is going to increase rapidly. I mean the vapor pressure, so that the vapor above the liquid is high, okay, and so it is going to become equivalent with the atmospheric pressure at lower temperature, okay, than the other one which is non-volatile. So therefore, when you are plotting, this is the mole fraction of cyclohexane, and maybe this is cyclohexane and water because they are non-volatile. Okay, so a mixture of cyclohexane and water, they are non-volatile. Okay, so this is pure water, for instance. This is pure water, and this one is pure cyclohexane. So you can see that 100% cyclohexane, it is more volatile. Okay, it boils at lower temperature than 100% water. Okay, and so as a result, you're going to get such a curve when you plot the composition, the different percentage composition of the mixture of cyclohexane. But if you are plotting vapor pressure, then you find when pure water is down and then pure cyclohexane will be up. Why? Because now this one is more volatile, so its vapor pressure increases so high at lower temperatures, okay, than the vapor pressure of a non-volatile component. So if we plot, then this is going to be the curve, whereby this one is going to be the boiling point of the liquid, and then this will be the vapor composition. So this is how the vapor composition of this liquid mixture is going to vary as you vary the percentage compositions. For instance, if we boil our liquid mixture that contains 50% of water and 50% cyclohexane, the mixture is going to boil at this temperature. Okay? It will boil at this temperature, giving off a vapor pressure that is equivalent to this. So this will be the vapor pressure, okay, of this 50% mixture of cyclohexane. That when we cool down this mixture, okay, with such a vapor pressure, then it will produce a liquid that has this composition. The liquid that will be produced is will have 80% of cyclohexane and just 20% of of water. This is 100% cyclohexane, and then this is 0% cyclohexane. So this is just water. So if you have 80% of cyclohexane, then it means you have 20% of water. Okay? Yes. Similarly, if we heat our liquid, okay, at this vapor pressure, sorry, if we heat our liquid with such a composition that we manage to distillate or to condense, our liquid, now because it has 20% water and 80% cyclohexane, then our liquid is going to boil at a temperature that is lower than the temperature at which a liquid mixture with 50% cyclohexane is going to boil at. You can have a look, you can see. Okay? It is going to be lower or it is going to be less. So if this one boils at 90, for instance, then this one will boil at something like 82. Okay? So as a result, so if it boils at this, then it will give the vapor pressure that is with this composition, such that when we cool this vapor pressure, now we shall form a liquid mixture with something like 95% cyclohexane. So the content, okay, the amount of cyclohexane is going to increase in the liquid mixture. I hope you can observe that. Such that with continuous distillation, okay, then we shall produce a liquid, a distillate that is purely cyclohexane and a residue that is purely water. Okay? Yes. So basically that's how cool, that's how simple this graph is. Okay? And we are going to meet questions and we shall be able to answer those questions. So let's talk about the concept, the principle of fractional distillation after having that deep insight, after having that deep understanding, okay, of a boiling point composition curve. So with fractional distillation, it is a principle Okay? It is a process by which two miscible liquids with different boiling points can be separated. And with miscible I mean the two liquids, they separate and form a uniform layer. Okay? You cannot separate you cannot tell which one is water, which one is ethanol, which one is which one is which. So the two liquids can be separated. Okay? Two liquids having different boiling points can easily be separated by fractional distillation. Now it is fractional if the boiling points are kinda. There is no that big difference between the boiling points. Okay? And because of that, then we shall use fraction. But if the difference is, if the margin is big, maybe one boils at 20 degrees Celsius and another one boils at 100 degrees Celsius, then this difference is really big. So we can just use simple distillation. So then how do we use fractional distillation? And how can we relate this fractional distillation with the curve that you just saw? It's just simple. You have your liquid, or you have your liquid mixture, okay, with such a percentage composition. And so you have your liquid mixture with such a composition. Actually, good, the composition is here. So you have A and you have B. So this is pure A and this one is pure B. You can have a look. So at 0% A, okay, then this one becomes pure B. And at 100% A, then this one is pure A. Alternatively, they can write more fraction instead of using percentage composition. Okay? And they write 0 here. They can say more fraction of A. And they write 0 here. And they write 1 here. Okay? So it means still, this is pure A. And this one is pure B. Okay? Now, pure A has it boils at this temperature. You can have a look. Okay? And pure B boils at this temperature. Okay? That's good. Now this graph is inverted, but let's just put these values down. We shall not use these ones up. Okay? Yes, let's put these values. So you have your B here and you have your A here. And let's say this one is something like you have a mixture of 70% A. Okay? And the mixture of 70% A, it is somewhere here. So if you try to boil this mixture of 70% A, that means it has 70% A and 30% B. This liquid mixture, it is going to boil at this temperature C1. Okay? Giving off a vapor pressure V1, for instance. Let me say V1. That when this vapor pressure is cooled, it is going to give a liquid mixture with such composition. Okay? Maybe you can call it M1. This is our composition, M1. Do you get the concept? This concept is really good and we shall encounter questions. Both here and we shall encounter questions. So the liquid mixture, maybe it has 70% A and 30% B. It is going to be boiled, like how you can see, and it will boil at temperature C1, giving off vapor V1, that when this vapor V1 is condensed, it will give off a liquid mixture with composition M1. And you can have a look that this liquid mixture here, M1, it has a composition that is rich now in B. Okay? Is it rich in B? So if this was pure A, then it means this is 100% B. Then it was a mistake. Let's make this one B. Okay? Let's make this one B, and then we make this one A. Okay? So you can see the composition of A in the liquid mixture is going to increase, whereas the composition of B in the liquid mixture is going to decrease. Okay? Why? Because since A boils at lower temperature than B, then A gives off a vapor, or the vapor pressure will contain more of A than B. So that when you cool, when you try to condense the vapor pressure, you will have more A in the liquid mixture than the B. So that when you carry out now, when you now distillate M1, it will now boil at a temperature that is slightly lower than the temperature at which this liquid mixture boiled at, giving off a vapor that has more of A now. You can see this is going to be the vapor pressure, that when you condense the vapor pressure, you get composition M2. Now further distillations, if you do fractional or if you fractionally distillate, okay, you can have a look. Fractionally distillate, you produce a distillate that has 100% A and 0% B. That's a distillate. And you produce a residue that has 100% B and 0% A. As simple as that. So guys, this concept is really good. It's really good, okay? That you shouldn't fail such like a simple question. So I think it's what I'm talking about here. No, it's not. So you have an example here. Can you please do that example, chap? I know you can. And you show me. So you're going to, they have given you the compound A has this boiling point, and compound B has this boiling point. And all of them, A and B, form an ideal solution. So you're going to sketch, okay, the boiling point composition curve, and then using that curve, describe and explain how pure B can be obtained from a mixture containing 50% A and 50% B. Guys, please do that. It's really cheap. It's really good. Okay? You can do it. Trust me. Yeah. If you can't, we can do it as an example. And you have another question. But we are here to practice. Practice as much as you can. Yeah, I've seen your work, and yeah, it was really good. Innocent, you did. Innocent, Jordan, yeah, Jordan, you did some good work. Others, though, you didn't show me, and I hope you tried. So you see, the question says you have A, and A boils at 380, okay, and B boils at 14. So between A and B, which one is more volatile than the other? Obviously, it's A, which boils at a temperature that is lower than that of B. I hope you are able to see that. Now, the question wants you to sketch the boiling point composition diagram. of this mixture. How the boiling point is going to vary with the composition. It's just simple work. Yes, I've created some space. It is just simple. So now, if we have our curves, okay, and this one is, the curves must have arrows, okay, and you have A here and you have B here, okay, and this one is more fraction, of, maybe you can say, B. So where this one is going to be 0 and this one is going to be 1. Then if this is the more fraction of pure B, so if this is pure B, then this one is going to be pure A. At 0B, then you have pure A. Now from the question you can see that A boils at a temperature that is slightly below the boiling point of B. So if this is the boiling point of pure A, okay, which is 380 degrees Celsius, okay, then the boiling point of pure B is going to be slightly above that of A. And so this is 410 degrees Celsius. Now, as the variation, as the mole fraction changes, maybe you have pure A here, but if you increase, okay, maybe the composition of this mixture from pure A to something like maybe 20% B and 80% A, then the boiling point is going to kinda increase. But if you have pure B and you increase the concentration of A, or you add some A, maybe the composition changes from 0A, something like 10A and 90B, then the boiling point decreases. So therefore, if you are to sketch the boiling point composition curve, okay, then the boiling point is going to take this part, and then the vapor pressure is going to have such a curve, where this is going to be the liquid phase, okay, and this one is going to be the gas phase, whereas this one is going to be the liquid gas equilibrium. Gas equilibrium. So it is basically as simple as that. Now, so this is our vapor pressure composition. No, this is our boiling point composition curve, and this is what we need. This is what we want. This is what the question wants from you. Now, using the diagram, this diagram of ours, describe and explain. The explanation is, okay, we are going to describe and explain how pure B can be obtained. So now we have, let me change a pen. You have a liquid mixture that is made up of 50A and 50% B. And you are required to separate this mixture so that you can obtain pure A and pure B. Obviously, you have to use fractional distillation, and this is a mark. You have to use fractional distillation, and this is a mark, whereby the two have different boiling points. However, the difference in the boiling points is not that much that you can use simple distillation. Otherwise, if the difference was much, like one is in 410, another one is in 100, then here we just need simple distillation, whereby you just boil once and you reach 100 and form a vapor, and you are guaranteed that this vapor is going to be 100% this. So the distillate is going to be the one which is more volatile, and the residue is going to be the one which is non-volatile. But here, the difference is not much. So we shall use fractional distillation. Now, why the difference? Why fractional distillation? Because when you heat up to this temperature, you can see, yes, you have more of A, but you still have some molecules of B. So that's why you distillate and distillate the distillate and distillate the distillate, the distillate, the distillate. Now that is confusing, which is okay.
It's your confusion.
Which is okay. Anyway, fractional distillation is you distillate the distillate and then again distillate the distillate that you formed. Anyway, so let's begin with 50%. Okay, so you have 50% A and 50% B. So if we heat this liquid mixture, it will boil at this temperature here. This one and this one. It will boil at that temperature. Not so? Yes. Now, the vapor pressure that will be above this 50% liquid mixture is going to be equivalent to this. That when you condense, when you try to condense this vapor, okay, you're going to form a liquid mixture that has this percentage. You can have a look, can have a glimpse, whereby it will have more of A and less of B. The mixture was 50 heated, but now the vapor is, it has more of A. Maybe this one can be like 30 B and 70 A. Now, why am I calling fractional distillation distillation of the distillate? This is our distillate now, but we still have 30% of B, but we want pure A. So we shall go ahead and heat. That's what we call distillate. So we shall go ahead and heat this liquid mixture here with such a composition, maybe M1. And when we heat this, it will boil at this temperature. You can see this one and this. That's the temperature at which it is going to boil. Now, at this temperature, it will give out a vapor with such a vapor composition, whereby it will have more of A. That when you condense this vapor, then it will give a liquid mixture with now more of A, something like 90% A. You can see? So we still distillate the distillate. We shall still heat this liquid mixture that will boil at this temperature, okay, giving out the vapor pressure of this, and the temperature at which it is going to boil is going to be this. So that when we do fractional distillation with further distillations, then we shall come up with a distillate that is purely A, and pure B is going to be obtained as a residue. And by that, you have separated the two components, having A and two components having A and B. So basically, it's as simple as this. Please, if you have any questions for me, please ask. Please ask. Okay? I beg, please ask. Yeah, so basically that's how simple it is. So now let's try out this. Okay? Let's try out this. And just few minutes. Few minutes should be enough to do this really. So if I try to interpret the question for you, you have the normal boiling point of liquids A and B as 80, and so between these two, which one is more volatile? which one is a volatile liquid and which one is a non-volatile. So the one which boils at lower temperature. So A is more volatile than B. I want to see your sketches. Now the mixture of A can be assumed to obey the Raoult's law. It is assumed that the mixture obeys the Raoult's law. So now the question wants us to show how the two substances can be separated by fractional distillation and explain the principle involved in the process, which is what that's what we've just done right now. Can I see at least you people doing some work? Hmm? Do some work. Do some work.